Hey everyone, today we are going to look at Intro to Audio Processing, or more specifically, how we work with audio to train neural networks. We're not going to look at neural networks today, we're mostly going to look at that pre-processing step of how do we get audio ready to actually pass it into a neural architecture. Working with audio is quite a bit different from working with images or text, so that's why I want to make this video. And also, we're going to just look at a high level how to use the TorchAudio package and how the different methods are related to each other. In future videos, we'll go in and actually look at some of the theory and implement these methods from scratch. So today is mostly just a use case, a practical use case of what's going on. So let's go ahead. Of course, if we're going to be working with audio, we need some audio to work with. So let's do that. NumPy as NP, import matplotlib.pyplot as PLT. And there's going to be a lot of copy pasting today because I mostly want to show visuals and y'all don't need to see me write code of making different visuals, but our main goal is to understand the TorchAudio package, at least some of the main methods that exist in it for us to use in the future. So we're going to import torchaudio.transforms st. This is just like your torchvision.transforms, but it's for audio. And then import ipython.display, and we're going to do from ipython.display import audio, and that'll let us actually visualize or play back one of the audio files. And so I already have an audio file in here that I've gone ahead and saved, so we're just going to take a look at that. And so our audio file is going to be for some audio, and it's going to return both the audio and the sampling rate, and that's going to be torchaudio.load, and we're going to go ahead and load our sample audio.flac. There we go. So that's going to be our audio file, and the audio file will sound like this: audio. We want to play back this audio, and the rate is going to be the sampling rate. And it should sound something like this.
A distinct promise of £100 was made to him if he would have the child ready to hand over.
Right, just some standard speech audio file. So first of all, if you've never heard of this term sampling rate before, the sampling rate is how many samples per second does your microphone capture. Basically, how many numbers are we using to represent the audio. So in this case, if we look at audio, audio is basically just a list of numbers. It's a number that changes over time. So it's kind of like a time series data set. And the sampling rate is how many samples do I have in every second of audio. So I have about 8 seconds worth of audio here. And the sampling rate of this file specifically is 16,000. So the sampling rate depends on the sensor or the microphone you're using to capture the audio. Higher quality microphones will have higher sampling rates, because they're able to capture more information in every second of audio. Now the sampling rate is important, and we'll talk about it later, but for now, for most neural architectures, we use about 16,000. Seems to be the standard sampling rate for most architectures out there. More modern ones and bigger models might use a slightly higher one, like 20,000, 22,000, 24,000. And we'll talk about why that's important in a bit. And so that's our sampling rate. Now typically when you look at audio, you see it in this form, plt.plot audio. And this will go ahead and create a nice little plot. Oh, yes, I remember. So our audio dot shape, notice it's a 1 by something. So plot's just trying to plot everything individually. That's unneeded. So we can do audio dot squeeze. And now this should work out fine. There we go. So this is our plot of a waveform over time, right? So it's basically sound pressure over time. That's what the microphones capture. And this is a standard figure you'll see when working with any kind of audio file. And this is known as the time domain of our signal because it's some value that's varying over time, right? This is the time axis, and this is basically our air pressure, right? The amount of air pressure axis. Now, this is a totally fine view of our audio, but typically this isn't the most helpful. Sometimes we're interested in the frequencies available inside an audio file. What do I mean by that? If you have taken a signal processing class before, you will have heard of the Fourier transform. If you've never heard of this before, go ahead and watch the 3 blue 1 brown video. It will visualize it way better than I could ever write it. But the main idea is you want to find out what are the frequencies that exist inside this audio file. And we're going to take a look at a couple of easy examples. The way I like to think about it is light. Light is a frequency. Different colors of lights have different frequencies. So if you take red light and you take blue light and you take green light, every single light has a different frequency. Now, if I take two different colors, like blue and yellow, and mix them together and get green, I can see that I have green light. But if I want to undo it and figure out what are the different colors that went into it, that's finding the individual frequencies that, when mixed together, create that green light. And so a Fourier transform goes in the opposite direction. It will take my green paint and undo it, figuring out what are the individual frequencies found inside that green paint, in this case blue and yellow. And so this is done by basically multiplying your signal by some complex exponential. I'm not going to go into any of the main ideas here, but it gives you a complex number that essentially represents the amount of energy at different frequencies, k. So let's go ahead and see what that looks like in practice. So let's first talk about frequency. You have heard of frequency before because this is something you'll see in standard calculus or pre-calculus courses or a trigonometry course. What we have here is a sinusoid at different frequencies. So we have a 1 hertz signal, and so that means we have 1 cycle per second. That's going to be in 1 second of audio, we have 1 complete cycle, as you can see with the blue line. Similarly, if we have 4 hertz, that means 4 cycles per second. So that means we have 4 complete cycles in 1 second. That's the orange line. And similarly, again, the green would be 8. Now, one thing I want to mention is this hertz, cycles per second, is different from this sampling rate, which is samples per second. Samples per second is how many samples or numbers were captured to produce this line. In this case, I have 1,000 numbers, 1,000 samples between 0 and 1. So I have 1,000 samples for 1 second. So this would be a 1,000 samples per second audio file. That's my sampling rate. On the other hand, we have 1 hertz. That's the cycle. So the cycles per second is about what's being captured. A low cycles per second is low frequency audio. So that's like very low pitched audio. And then you have high frequency audio. That would be much higher frequency audio, right? Higher frequency audio. And so that's the way to think about it. There's 2 different frequencies going on. There is a relationship between them called the Nyquist rate that we'll talk about in just a bit, but just keep that in mind so you don't get them confused. So we have here cycles per second, and our goal is to be able to identify what is the frequency, the cycles per second of a sinusoid, and the Fourier transform provides that to us. And so let's go ahead and see what that looks like. Again, a lot of copy pasting here, but let's just go ahead and add u in first, and then we'll do the rest of it. So what I've done is created 1,000 points between 0 and 1. So that's t, right? We have 1,000 points here between time 0 all the way up to non-inclusive time 1. So there we go. And what I'm saying is I want a sinusoid with a frequency of 20. Okay, no problem. We can do y is equal to np.sin. And this is your standard sinusoid formula, 2 times pi np dot pi times your frequency that you want times the time, right? This is your standard formula. So if you do plt dot plot y, you'll end up seeing in 1,000 samples, we have 20 repetitions, right? 20 full cycles happening. And here it is in the sampling rate view, right? We have 1,000 samples, or we can do it in the time view. And that's going to be if we do t comma y. That's going to be in 1 second, we have 20 different cycles happening. So just some things to keep in mind. And our goal is to find out what is the Fourier transform of this, and what does the Fourier transform provide us? What kind of information do we learn from it? So if we do y, FFT, it's going to be np.fft.fft. So this is the standard NumPy fast Fourier transform that we can look at. So FFT, and we're going to take the Fourier transform of y. And when we look at y FFT, what we see is we get a bunch of these complex numbers. And what do I mean by complex numbers? Well, it has a real term. So you can see it's 1.2 e to the negative 14, so basically 0, plus a complex term, right? Because you can see there's this j attached there. So these are your standard complex numbers in the form of a plus bj, right? So complex numbers. And this provides us how much energy and the phase, so there's a magnitude and a phase component, which we'll talk about in a bit, but just for now, it's essentially how much energy is available at this frequency component, how much energy is in this frequency component, how much energy is in this frequency component. And the question you may be asking is, well, these are energies, but what frequencies do they represent? So what is the frequency of this one? What is the frequency of this one? ... And so we can easily compute that, or we can just use one of the built-in functions from NumPy. Frequencies is going to be np.fft.fft, and it's going to be, and this is going to be FFT frequency. And all it needs is to know what is the, how many samples do we have in our thing, and then we can say d equals the time between samples is just going to be how much time at t1 minus t0, and we know that there's 8,000 samples, so this would be 1 over 1,000, right? The distance between the two. So we could have also done that. Yeah, there we go. So these are my frequencies. I have frequency 0, so basically 0 cycles per second, 1 cycle per second, 2 cycle per second, 3 cycle per second, ... And we know our signal, the original signal that we applied the FFT to, has 20 cycles per second. So we're expecting something special to happen here. And so we'll see that in just a bit. And so these are my frequencies. You can also see we have both positive frequencies. We also have these negative frequencies, right? Negative 96, 97, negative 20, ... And negative frequencies are not all that interesting to us, so we'll see what that looks like in just a bit. And so, actually let's just go ahead and plot it. plt.plot. If we plot our, let's just go ahead, so let's just look at it right here. We have here our complex numbers, right? Each complex exponential is just, it creates a complex number of a plus jb. And this complex value has two things. It has a magnitude and a phase. And the magnitude is what we really care about. It's the energy at which, the amount of energy at that specific frequency. But the phase is basically what we have right here, right? The angle itself. So every complex number always has a magnitude component and a phase component. We don't really care about the phase all that much right now, but it basically tells us the shift of that frequency component. So let's just take a look and see what it does. So if we do plt.plot and we plot our, on our x-axis, let's plot our frequencies, so freaks. And on our y-axis, let's plot our actual values, the complex values, but we can't plot a complex value, so we can plot the absolute value of it. This will provide automatically the magnitude. So if you do .abs on complex numbers in NumPy, it'll basically go ahead and do this. If you did .angle, it would provide you the phase, but that's fine. .abs, oh, right, not abs, np.abs, there we go. Right, so we can see that we have all of these frequencies available to us. We can see it kind of goes from negative 500 to 500-ish, and we have these two peaks, right? A spike here and a spike here. The thing is that we don't really care about negative frequencies. It's just that when we do the Fourier transform, every positive frequency from our complex numbers, every positive frequency identified also has its negative complex conjugate, right? That's just the way that Fourier transforms work. Everything comes in pairs. There's a complex conjugate. We just don't care about the negative side, so we can just ignore them, right? Let's just ignore them. So we only want the frequencies that are the positive ones. So let's go ahead and change that to only show the positive ones. So that would be, it'll be from, let's just index them. It'll start in the middle. So we basically need to start from the middle. So that's going to be the len of frequencies divided by 2. And then similarly, it's going to be the len of frequencies divided by 2. And so now we have our only the positive section, the positive frequencies. And notice that we have a spike at about 20 hertz, right? And we have no other energy at any other cycles per second. And that's because the signal we applied this Fourier transform to was a 20 hertz signal, 20 samples per second. And so we're able to identify what is the overall frequency of this specific signal. And which is pretty neat, right? We're able to kind of extract that information. And so now that we have that, there is one limitation, and this is what I'm talking about, the relationship between the sampling rate, the samples per second that your microphone captures, and your signal rate, the cycles per second, right? The frequencies that the microphone is capturing. And the main idea is that if your samples per second is, let's say, 1,000, like we've had it up till now, so your microphone is capturing 1,000 numbers every second, the maximum number of cycles per second that your audio can represent is only 500. So it's always half. So your frequency of a signal is always represented, the max that it can represent is half the sampling rate. And so this is helpful, but it does lead to some issues. So the reason this matters, first of all, is that your human hearing can hear up to about 20,000-ish hertz, right? So 20,000 cycles per second is the highest pitch that we can understand. This means that our audio files need to be at least 40,000 samples per second, right? Samples per second. So our microphones need to be able to capture 40,000 samples every second to contain all of that information. Because if our microphone's capturing 40,000 samples per second, then the highest frequency that that microphone can represent, that audio can represent, would be 20,000 samples per second, 20,000 cycles per second, because that's half. So that's the important part. Now that is a theoretical limit, because it's never perfect. So if we have 40,000 samples per second, we can technically represent up to 20,000 cycles per second, but it's not perfect. So that's why typically you'll see 44,100 samples per second in high quality microphones, right? That's kind of why, because it gives you a little bit of buffer room over the kind of the perfect Nyquist rate. And so now that we have all of this, we can go ahead and take a look at a common problem known as aliasing. So aliasing happens when we downsample audio, and this happens all the time when you're working with data. For example, let's say that you are working with some audio that has high frequency information. Let's say the audio has, and let's go ahead and write it out so it makes sense. Let's say you're working with audio that has 10,000, and it's going to be cycle per second. So this is my high frequency information. And let's say I captured it pretty well at, let's say I was recording with 24,000 sample per second. So if I'm capturing at 24,000 samples per second by the Nyquist rule, right, Nyquist, I will be able to represent up to 12,000 cycle per second. So that's good, right? I'm able to represent up to 12,000, which is no problem, because if the max, right, if I know the maximum is 10,000, no big deal. We are able to capture all of that audio information, all of that frequency information with this sampling rate. So we're good to go. Now, what I said was that neural networks are typically trained on 16,000 samples per second, right? Like wave to vec will be one of the architectures we look at. It's trained on 16,000 samples per second, which means we need to do a downsampling, right? Downsample. And this downsample is the same as if you start with an image, right? So if you've worked with images, let's say you start with ImageNet images that are 256 by 256. That's an ImageNet image. And then, but we know our neural network takes 224 by 224, 224 by 224. We end up losing a little bit of resolution because we're downsampling the image. Downsampling in an image has the exact same Nyquist properties, but we don't really think about it when we do it in images as much. But we have the same problem here in audio. We're going to take this 24,000 samples per second, and we're going to end up taking the, and we're going to downsample it to 16,000 samples per second. But now, if we do Nyquist again, Nyquist, the maximum thing that my 16,000 samples per second can represent would be 8,000 cycles per second. And we have a problem, because in my original audio of 24,000 samples per second, with my 12,000 max, I was covered because I know 10,000 was the most in my data. But now that I've downsampled my audio from 24,000 to 16,000, the max I can represent is 8,000, which is underneath the 10,000 that I need. So this 10,000, basically all the frequency information between 8,000 to 10,000 hertz that was in my original audio will get aliased. And so you end up losing that frequency information because your signal just can't contain it anymore. So it has to go somewhere, and so it gets aliased down. And so let's go ahead and take a look at what that looks like. So what we're going to do is we're going to create a audio file, or basically a sinusoid, just like we did before. And what we have here is and this would be 200, we have a 200 samples per second audio, right? So if it's 200 samples per second, I know the maximum thing I can represent is 100 cycles per second. So I know it's 100, but I pick 40. So 40 is under 100, so we're good to go. So I go ahead and create that sinusoid. And what we're going to do is just apply the Fourier transform to it, just like we did earlier, nothing new. So we're going to go ahead and provide the Fourier transform, everything same as before, nothing new. And now what we're going to do is downsample the audio, right? We're going to downsample. So we're going to do a downsample factor. It's going to be, let's say, a factor of 4. Yeah, let's do a factor of 4. So that means we're going to go from 200 hertz downsampled by a factor of 4. So it'd be 50 hertz. So we have 50 samples per second. But if we have only 50 samples per second, so this is going to be 50 sample per second, which means that the maximum cycles per second that I can represent is half. That'd be 25 cycle per second. The problem is 25 cycles per second is less than the 40 that I have in my original audio, right? The original signal. So let's see what happens to that. So what we're going to do is downsample our audio. That's just going to be T low is going to be equal to T high. So we're going to downsample both my time. So we're going to take every other time step and our data itself, T high, and we're going to do downsample factor, right? We're going to skip every step. And then similarly, we're going to do y low is going to be, and this is y basically, low is downsample. It's just going to be the y high, again, downsample factor. Right, so I've gone ahead and downsampled everything by a factor of 4. And then just like before, we're going to go ahead and apply our Fourier transform to the downsampled data. Right, so go ahead and apply the Fourier transform, get the frequencies of the downsampled data. So there we go. And now let's go ahead and plot it. So again, I'm not going to make you watch me create some plotting functions. So here's my original signal. I had, and this shouldn't be 80 hertz. This should be 40 hertz. My bad. There we go. 40 hertz. So I have 40 cycles happening in 1 second. But because I downsampled my signal by a factor of 4, now you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cycles happening in the same amount of time because we've downsampled directly by a factor of 4. And here's the aliasing effect. I had a signal that originally had energy at 40 hertz. Now that my downsampled signal can no longer represent that information, it gets aliased down. So we can only represent that 40 hertz frequency gets aliased down to here instead. And so this is you losing that frequency information. And why it's really important to keep in mind, what are the general frequencies that your audio is working, that your audio contains, and make sure that when you do any kind of downsampling of your signal, that you still maintain that information in there. So these are just kind of good ideas to keep in mind. Now, what would be interesting here is what if we change our downsampling factor to 2? If we change to 2, that means we're going to go from 200 hertz, right, 200 samples per second. So if we do this to 2, that means we'll only go down to 100 samples per second, right? We're going to go from 200 down to 100 because we've only halved, which means the highest frequency cycles per second we can represent is half, and that would be 50. Luckily for us, 50 is greater than the 40 we were working with. So we should see no aliasing happening now. So let's see if that's true. And you can see exactly that. We lose some energy, like magnitude, but that same frequency is still represented. So we haven't aliased that information away. Right? All right, cool. So that is your main, should be the main takeaway about aliasing. So let's just keep moving. Like I mentioned, at the beginning, the whole point of a Fourier transform is to basically undo mixed paint, right? And so what happens if you take a couple of different signals, with 3 different frequencies. So we have a sinusoid at 5 cycles per second, 20 cycles per second, 40 cycles per second, and we just add those signals together and then do the Fourier transform. Well, basically the same thing. Here's the sum of your sinusoids, and the Fourier transform is able to identify energy at 5 hertz, energy at 20 hertz, energy at 40 hertz. Right? So we're able to find those frequencies here. If we add another one, let's say we add one at 250, then we'll end up with kind of a signal that looks like this, but we have 5, 20, 40, and then here we go. We have one straight at 250. So the Fourier transform again is able to identify the energy at the different frequencies available in our signal. And so that's the fun part. Now, of course, if we do a Fourier transform, and the Fourier transform goes from the time domain signal, where the x-axis is time, to the frequency domain, which the x-axis is the frequency. If we can go in one way, then we should be able to go the other way, right? The inverse transform. And this is as simple as just doing the inverse transform, which I can just go ahead again. Same code as before, adding together a bunch of sinusoids, do the Fourier transform, but after you do the Fourier transform, do the IFFT, inverse Fourier transform. So in the exact same way, here you go, you have a signal, you take its Fourier transform, and then you take its inverse Fourier transform, and these two signals should be identical to each other. And there we go. Now, here's the problem with a Fourier transform. And let's kind of think about it this way. I'm going to apply the Fourier transform to our actual audio. So if you remember up here, we had our audio file. This audio file contains lots of different frequencies, right? Lots of different frequencies. And so what we want to do is apply the Fourier transform to this and just see what that looks like. So I called it audio, so that's what we're going to do. All we want to do is basically this code right here. We're going to apply U to our audio instead. So instead of the sum of sinusoids, let's get rid of that, we're going to do it on our audio. And T, it's going to be len audio, and we know that our audio sampled at 16,000 samples per second. So the distance between time, or the, is going to be 1 over 16,000. And so we end up with, and let's change U to audio, and there won't be a T here. This will be range audio. Oh, right, we have to do list range audio, make sure it's an array. Only integers of a single element can be converted to an index. Here, let's just do audio. Here we go. So we have our audio file, just like that. This is and this is no longer the sum of sinusoids, so these titles no longer are correct. So let's get rid of that. There we go. So this is the audio file that we are working with, and here are all of the frequencies that are available in that audio file. But this view is not actually all that helpful to us. Like, sure, we have the frequencies, but notice that audio files, unlike the signals we were working with here, because this signal here kind of repeats and it's, it's very repetitive, it's periodic. The audio file, there's clearly some change happening over time. Like in these areas, like the empty areas, we have low frequency, like nothing's happening here, so it's low frequency. In these areas, there's lots of change happening, so this is a higher frequency. And because there's kind of this mix of low and high frequencies and things are changing over time, we lose that, because in the regular Fourier transform, we go from the time domain squarely into the frequency domain. Like it's a full conversion to the frequency domain. And the inverse Fourier transform goes backwards. But is there any kind of middle ground that we can do where we have both time and frequency information? And yes, that's exactly what we're going to do. This is known as the spectrogram. And the spectrogram is known as it's basically like a picture of the audio. And hopefully this will make sense. Before we do it in TorchAudio, we're going to go ahead and do it in SciPy, because SciPy will provide, again, remember, a Fourier transform provides us both let's scroll back up just to make sure, it's a complex number, returns a complex number, which means we can get both the magnitude and the phase information. Both of that's available to us. It's just, up till now, like what we're looking at here, all of this stuff is just the magnitude, because typically we just care about the magnitude, about how much energy is there at the different frequencies. Either way, let's go ahead and take a look at what this produces. When we apply the Fourier transform, the short time Fourier transform, so the short time STFT, short time Fourier transform, produces something known as the spectrogram. And the spectrogram we'll talk about a couple things in just a bit, but it produces both the magnitude and the phase. But notice here that things are a little bit different, where we have a time and a frequency axis, right? Time and a frequency axis. Whereas opposed to before, we just had frequency, or we just had time, and we just had the magnitude along, our y-axis. And so because we have time and frequency axis, we can see both things at the same time. We can see along this time, you can see at the beginning part here, so let's look at the original audio. At the beginning part here, there's basically no information, right? It's basically silent. Is that true? At this beginning part here, notice that there's no frequency information, very low frequency down here. But then once talking actually begins, you can see a spike happen here and some speaking occurring. You can start to see some frequencies being represented. And honestly, what's more interesting is you can see the changes in the different frequencies. And what's extra cool is there's a clear relationship between the shapes of how these frequencies are changing, right? You can see here there's a decrease, here there's like an increase and a decrease, here there's the different shapes of how these frequencies occur, and the phonemes, or basically the phonetics of what's being said. So once you get really good, which I'm definitely not, but once you get really good, like my professor, can look at this and give you an idea of what's actually being said from just the shapes of the frequencies, which is really neat. And so this is our spectrogram magnitude, but of course, a Fourier transform, whether or not the regular Fourier transform, short time Fourier transform, whatever it may be, gives us two things. It gives us a magnitude plot. We can produce the magnitude and we can produce the phase. It's just that, as you can see here, the phase there's no discernible structure in this image here. It seems kind of like noise. I mean, it's not. The phase is important, but it doesn't really give us the information that we're looking for. And that's why typically when we're working with spectrograms, we only deal with the magnitude plot, the amount of energy at the different frequencies at the different times. And so that's the key takeaway. That's why I use SciPy here, because in the TorchAudio, they basically just return this magnitude spectrogram. They don't even return the phase. But SciPy gives us both of them, so we can take a look. Now, what are the things that you have to think about when creating a spectrogram? There's two things. There is the number of samples per segment and then the number of overlap. So first of all, in a spectrogram, it's still doing a Fourier transform, it's just doing it slightly differently. So if we look at this audio here, what it's doing is it's going to take a Fourier transform of, instead of the entire signal at once, it's going to take the Fourier transform of small chunks of the signal at a time. And then, for example, let's say we do let's say our number of, our length of the segment, here it's 400, let's say it was 20, or let's say it's 20,000. That means I do the Fourier transform of the first 20,000 samples only. And then we have number of overlap. So when we do the next chunk, if the overlap was 0, then we do a Fourier transform of 0 to 20,000, 20,000, 40,000, 40,000, 60,000, 60,000, 80,000, ... So we do a Fourier transform on these different chunks of the audio. And then we do a Fourier transform here, and we'll produce some type of a regular Fourier transform here. And this here becomes one of our columns of this, basically one of those bins. And we'll see what those bins look like in just a second. So those are our bins. And the interesting part is, as you kind of reduce your Fourier the length of these windows that we use, you get different pieces of information. So there is a little bit more nuance to this, like how do you window it? There's Hamming windows, Hanning windows, stuff like that. I'm not going to go into those details today. You can find those online, and we'll look at them later when we implement the short time Fourier transform. But the main idea is we have some audio that we're applying some Fourier transform to on different chunks of it. The other key idea is we don't just apply Fourier transform to different chunks, but rather we do them to slightly overlapping chunks. And this is meant for two main reasons. First, it gives a better representation because of the windowing process, because if we just apply a Fourier transform to one chunk of an audio, you'll have an abrupt start and an abrupt end. And this is why we'll use something like a Hamming window to smooth it out. So I can pull a picture of that up. Hamming window looks kind of like this. Basically, we take a signal. We take our signal that we're working with. We take the chunk that we have, and we're going to multiply that chunk by this Hamming window. So the start of the audio and the end of the audio is kind of dampened out. And so it leads to a bunch of cool properties. Like, here we go. If you have this signal here and you apply this Hamming window, you end up with kind of a decayed version of the signal, kind of like this. And this allows us to get smoother properties, smoother calculations of the Fourier transform. So that's one thing. But because we do that, we end up having to do an overlap add method. So when you do the inverse short time Fourier transform, it uses a method called overlap add. We're not going to go into too much of that today, but that requires some type of an overlap. So instead of just saying, I want to do 0 to 20,000, 20,000, 40,000, you might have an overlap of 10,000. So you'll do from 0 to 20,000, then you'll do from 10,000 to 30,000, then you'll do 20,000 to 40,000, then you'll do 30,000 to 50,000. So you'll have a 10,000 sample overlap between the different Fourier transforms you're doing. So that's neat. Now that we have that, let's go ahead and look at the time frequency relationship. What happens when I pick a very large size for this? So let's go ahead and set it this way. Let's do our window size. Right now it's 400. And so this is going to be window size. And our overlap is typically half the size. So it doesn't have to be half, but half is what you typically use. So we're going to be doing half the window size will be the overlap. So we'll do window size divided by 2. So this is what we had so far, right? 400. Let's see what happens when we increase it. Let's say we make it 10,000. What do you notice here? We have very good frequency resolution. Notice how many bins. We go from 0 to 8,000, right? Our frequency resolution is quite high, but it's kind of blurry, like it's stretched out because our time resolution is pretty poor, because each bin is so large that you can see that basically every bin takes up quite a large chunk of time. So you have poor time resolution because every window is 10,000 long, but very, very good frequency resolution, right? Very good because we can see all of the frequencies that are being represented, because that's just how we're doing it. On the other hand, what happens if we pick a very small window size? Let's just say 16. We'll have exactly the opposite problem. We're going to have very good time resolution because every Fourier transform we take is just on a tiny little section of audio. But because we're doing Fourier transforms on such small segments, we get poor frequency resolution. You can count 1, 2, 3, 4, 5, 6, 7, 8 bins, right? Because if you have 16 things, we only want the positive frequencies. That means we're going to end up with 8 bins here, 8 frequency bins. And so this is your clear trade-off between your time and frequency resolution, right? So small window sizes lead to good time resolution, but very poor frequency resolution because we lose that kind of the inner details of the frequency. And then vice versa. Large window sizes lead to poor time resolution, so we kind of lose the how things are changing over time, but we get a very strong frequency resolution. And so this is the main thing to keep in mind when you're working with it. And so just picking a reasonable number here is often a little bit of an art, but for the most part, for at least speech and stuff like that, there's good defaults. Like 400 seems to work pretty well, so we're going to go with that here. We could try something else. We could say like 1024. I'm not entirely sure. So this is what it looks like at 1024. You can see you get slightly better frequency resolution, right? These lines are more clearly marked out of how things are changing, but we have a little bit worse time resolution. So again, it's a little bit of a science, but there's good practices for most types of data that you're going to work out there on. So we are good to go. Now we did this with the SciPy. Let's go ahead and just do it with TorchAudio so it's very clear. So in TorchAudio, let's go ahead and set this up. So this is going to be a transform. It's going to be t.spectrogram, right? t.spectrogram, and FFT equals 400. Hop length is equal to 200, right? So that's the one that I used earlier. And we're going to do spectrogram. It's going to be transform audio. We're going to take our audio, apply that transform to it, and let's go ahead and plot it. And when we plot it, you end up with something like this, which obviously is not very helpful to look at. Like, there's not really a lot of information here. And that's because we're looking at the raw amplitudes. And it's very common to take the raw amplitudes here and scale it, typically log scale it. So what we're going to do is convert it to decibels. And so decibels, very clear formula, we can just take the log of this thing and multiply it by 20 and we'd be good to go. But let's just go ahead and learn a couple of the transforms available to you. So that's going to be dB transform is equal to t dot amplitude to decibel, right? It's another formula or another method built right into TorchAudio. dB spec is going to be equal to dB transform spec. And so again, let's go ahead and just plot this out. Let's get rid of that. And now we get something that looked like what we had earlier, right? We have our actual decibel values here. And just like before, if we change this to, let's say 1024, so notice the frequency resolution, it's a little bit, we have good time resolution, but frequency resolution, we can see like we have a little bit of blurring, I guess, along the frequency dimension. So look how thick these bands are, these frequency bands. If we change it, let's say 1024, and this will just be half, so 512. And again, do this, we end up getting slightly better frequency resolution, but slightly worse time resolution. So what you use kind of depends on what you're trying to solve for, and honestly, how much frequency information is in that data, but that's the main idea. Now let's talk about Mel spectrograms, because spectrograms are useful, and they're useful in basically any domain, but most types of data has something special that we can do with it. And Mel spectrograms are closer to what the human ear perceives, because it's an approximation of our auditory perception. So the reason is that our frequencies here are a linear scale, right? It's basically linear, like you have 0 frequency, 100, 200, 300, 400, 500, whatever it may be. We have some linear scale here for the frequencies. But human hearing does not work linearly. So we need a better approximation of that. It's not that you couldn't use the spectrograms, it's just Mel spectrograms are better built for human hearing, human speech, that sort of stuff. And how it works is this. Basically, we have this formula. This was basically, they ran a study, they collected a lot of data of how people perceive audio, and then they fit a regression model, and that's where these coefficients all come from, right? They fit a model to it to figure it out. And this is what it looks like, this plot. And so what it says is that, notice that when you go from 0 to 2500 hertz, right? So when you increasing in your frequency, raw, true frequency values, in the low frequency range, we get a pretty good increase in the frequency in the Mel frequency range. On the other hand, in higher frequencies, the same increases, so going from 0 to 2500, led to a 0 to almost 1750 increase here. But that same amount of increase from like 17,500 to like 20,000 leads to a much smaller increase in the Mel frequency range. And why would that be? So let's take a look. This is essentially the power law of perception. So there's a lot of ways to think about it. Let's think about it in terms of cars first. If you're driving a car at 10 miles an hour and you increase by 10 miles an hour, so now you're driving at 20 miles an hour, you feel like you're going faster, right? Because you've doubled your speed. So you feel like you're actually going faster. On the other hand, if you're driving at 60 miles an hour and increase by the same 10 miles per hour, so this is now 70 miles per hour, going from 60 to 70 miles per hour doesn't feel like a huge increase because it isn't, right? It's absolute, it's the same. You've increased by 10, but proportionally it's much less because you haven't doubled it. To get that same effect, you'd have to go from 60 miles an hour to 120 miles an hour, right? To double your speed. And so this is the power law of perception. Okay, so let's see why this happens. So what we're going to do first is our samples per second. Most microphones record at 44,100, so that's what we're going to use here. And then let's do our frequency is going to be 440, right? So this is, I believe it's middle C, but either way, that's a standard frequency that we'll test right now, 440. Duration is going to be let's say 10 seconds of audio. And so then we're going to do our T is NP dot A range, and it's going to go from duration, or let's do duration times samples per second, right? So that's our times, all the times that we need. And then we can do our waveform is going to be np.sine, standard formula from before, 2 times np.pi times our t, and this will be t divided by, because this is just 0 to whatever, it needs to be divided by the our number of samples per second, so we get the correct indexes, so it goes from 0 to however many seconds we have. So there we go, t times our frequency. And so we do plt.plot waveform. We'll see, this waveform, not very helpful to see that, but we can play it back. We can do audio, it'll be the waveform, and our rate is going to be the samples per second. So you should hear that, right? That's our sound. And what we're going to do is let's mess with this a little bit. So let's set the frequency to be 200 right now. So this is our frequency, right? 200. Let's say we increase it by 200. Let's make it 400. Okay, we can hear a pretty good difference between those. Now let's do the same thing. Let's do 1000. That's 1000 hertz. But then when we do 1200, it's not as big of a difference. It doesn't feel as big of a difference. And let's do another one. Let's do 2500. Sorry if it's a little loud. And then we'll do 2700. So it's a 200 increase. It's a very little bit of increase because perceptually it doesn't seem like much more. And so this is exactly what the Mel frequency, the Mel scale does. It puts less of an increase in changes in higher frequencies. And so our first goal is to convert this spectrogram here to the Mel scale, so it's more accurate or closer to how human hearing works. Luckily, to do that is pretty straightforward. We can just use the transform from our TorchAudio transforms. A transform is going to be t.Mel Spectrogram. And let's just provide it. The sample rate is again 16,000 in our audio. And FFT, let's just say 1024, it doesn't really matter. Hop length is equal to 512, because before our Mel spectrogram can be created, it first needs to create the spectrogram. So these are the spectrograms. And then we have our n Mels. And this is the number of Mel bins that we want to use. How are we going to bin these frequencies into the different Mel groups? And that's kind of up to you. You can have only up to so many. So you can have n Mels up to the number of frequency bins from the FFT. So if your Fourier transform gives you 500 frequency bins, then you can have up to 500 Mel bins. But typically we use a slightly smaller number to aggregate that information a little bit. And so let's just do 128 here, right? Again, the specifics of how this all happens we'll implement another day. Today's just to give you an idea of what's going on. And 128 is a pretty typical value we use for most speech models. So that's where we're going with it. And there's actually two different types of Mel scales that are slightly different from each other. There's Slaney and HTK. We will just use Slaney today. So that's our transform. And so let's go ahead. Our Mel spectrogram is just going to be the transform on that audio, which will first compute the spectrogram, and then it will apply the Mel scale to it. And then once we have that, everything else is the same. So we can go ahead and copy it in. We're going to convert it to decibels, right? And then we're going to go ahead and just plot it. And we end up with something like this. So we get this Mel scale. Notice that it goes from 100 or 0 to about 128. And this is a better representation of human speech. Let's compare it to earlier. Notice that we have a linear increase here. So all of our frequency stuff is kind of, all of our frequency information is kind of compressed down here because it really doesn't go much higher. But we know that as we increase in our frequency, we should have more emphasis at these changes in the lower frequencies should have more emphasis. And that's why it's essentially stretching it out a little bit more. So your low frequency information from here, these changes in frequencies should be accentuated, right? These differences in these frequencies should be accentuated more. So the Mel frequency essentially just stretches them out a little bit more. And that's why we end up with something like this. It's just a scaling factor. It's nothing, nothing crazy is going on. It's mostly just rescaling our frequency axis, but that's it. So now that we have our Mel spectrogram, the last part is how do we go from this back to the audio? So remember again, to do our inverse Fourier transform, which we did right here, inverse transform, we went from the raw Fourier transform, right? We passed in YFFT back into the inverse Fourier transform. And YFFT here were complex numbers, right? So when we apply the Fourier transform, we get both the we have both the magnitude and the phase information incorporated in those complex numbers. So that's the key idea. The problem is, when I mentioned here, when we did this spectrogram here, we had both the magnitude and the phase information. So no problem here. We could totally invert this because this ZXX, right, our short time Fourier transform has complex numbers. So as long as we have the magnitude and the phase information, we can invert it. The main issue is that I mentioned how the phase technically is not used and we only use the magnitude. And if you only have the magnitude plot, then there's actually no way to invert it, not directly at least. And so we have to use a trick. If we only have the magnitude information, and basically all neural networks are only, as far as I can tell, most neural networks are using just the magnitude spectrograms, then we need to have another trick to invert it, because we don't have the phase that tells us the alignment of these different frequencies. And so if we don't have it, we need to use a trick, and that trick is known as the Griffin-Lim algorithm. And so a clear place you would use this actually is a text-to-speech model. So a text-to-speech model is something where you provided some text and it generates some speech. But most actually not most, but a lot of models out there are not directly generating this raw waveform. What they're generating is this Mel spectrogram. And then given this Mel spectrogram, we can invert it to the speech that we're interested in. So that's the key idea here. In which case, if we're doing this, then what we can do, then the problem is, how do we invert this when we only have the magnitude? If we only have the magnitude Mel spectrogram, then we have no way to invert it, because the inverse Fourier transform requires that we have both the magnitude and the phase. And so this is what the Griffin-Lim algorithm overcomes. It uses essentially a back and forth projection, an iterative projection method, to retrieve the phase of the spectrogram. The procedure is that we start with, if we don't know what the phase of the different frequencies are here over time, then why not just pick a random phase, invert the STFT with those random phases, that current phase guess, back to the waveform, and then take the short time Fourier transform again of that, rescale the magnitude, and then repeat when converged. Again, we're going to take a look at a little bit of the math and the implementation in the future of how we actually build this, but we're just going to basically do a bunch of iterative, take a short time Fourier transform, take an inverse short time Fourier transform. Just keep going over and over again until our phases converge. The reason this actually works is because, again, of that overlap add method. Because if I take a short time Fourier, if I take a Fourier transform of this chunk right here, and then this second chunk right here, and we'll end up with this small bit of overlap between the two. And if we have an overlap, regardless of how many Fourier transforms and short time Fourier transforms that we take and inverse Fourier transforms, no matter how many times we go back and forth between the time domain and the frequency domain, these values have to be the same. And so it's a constrained optimization, essentially, where we want to basically keep taking the transform, the Fourier transform, and the inverse transform over and over again, and ensure that these values end up converging to be the same, which will only happen when the phases align. So that's kind of a high level of why it's working, but we'll look at that in more detail later on. So for us to do this, the Griffin-Lim algorithm actually only works directly on the original spectrogram, not the Mel scale. So we have two steps. We need to take the Mel spectrogram, we need to unconvert it back to regular spectrograms, and then once we have regular spectrograms, we can apply the Griffin-Lim algorithm to that to get our final result. So let's go ahead and just copy the part that's the same from before. So we have here our waveform, we have our Mel spectrogram, and we've created our Mel spectrogram. Now, here is the first takeaway. Let's go back up here, and this is going to kind of allude back to what we had looked at earlier. If we look at our, let's see here. Let's look at the print. Let's just print the magnitude. Print magnitude dot, actually, maybe let's do it in the next one where we do it right here. Let's print the db spec dot shape. Notice that the shape here is 513 by 275. 275 is along the time dimensions, but we have 513 here. Where did this 513 on this spectrogram come from? Well, remember, this spectrogram used a FFT length, the window length, of 1024. So that means we have 1024 frequency bins in every single chunk, right? Every single chunk, we have 1024 frequency bins that we end up creating. The thing is that half of those frequency bins are negative frequency, and the other half are the positive frequencies. We typically only care about the positive frequencies, which is why this has 512 plus 1 for the DC term, right? 0 frequency. So we have 512 plus 1, so 513 frequency bins that are had. Because all of the other frequency bins that would be on the other half, right? They keep going in the negative direction. They would just be exactly the same as this. It'd just be a reflection of the same data, just on the other half. And which is less interesting to us, right? We don't really care about the negative frequencies, so we just have the positive frequencies. And so that's where this 513 comes from. And so that will make more sense why we need that right here. So now that we have this Mel spectrogram, what we want to do is convert this Mel spectrogram back into the original spectrogram. So how do we do that? This is going to be inverse Mel scale transform. It's going to be t dot inverse Mel scale. And this is going to need a couple pieces of information. First, STFT. How many frequency bins are there? Well, we have 1024, but we only will be computing for the positive ones. So that's going to be 512 plus 1, 513. So that's why we have 513 here, because we only want to keep the positive and the zero frequency term. And then how many mels do we have? N mels. Well, we set that ahead of time, right? We set 128 mels, so it just needs to know that, oh, the signal coming in has 128. And then, of course, we provide the sample rate is the sample rate. And then we provide the Mel scale that we used. In this case, we use Slaney, so we're going to let it know Slaney here. And this will go ahead and invert our spectrogram. So we're going to go from Mel spectrogram to regular spectrogram. It's going to be our inverse Mel scale transform of our Mel spectrogram. Right, so that's our inverted spectrogram, nothing crazy. And now that we have a spectrogram, notice these are magnitudes, right, it's values, but we have no phase information. So there's no way for us to do an actual inverse, right? We can't do the inverse short time Fourier transform. So because we can't do that, what we're going to do is go ahead and use the Griffin-Lim algorithm to iteratively estimate those phases and get the reconstructed waveform. So we're going to do Griffin-Lim transform is going to be t dot Griffin-Lim and FFT. So how many frequency bins are there? We know there's 1024, right? That's what we set it to. Hop length is going to be, in this case, it's going to be 512, right? We want one half, as we set it up here, right? 512 is our hop length. And then how many this is an iterative algorithm, so how many iterations do we want to use? Let's just do 100 for now, right? Basically, it'll keep going until convergence. And so now we can finally go ahead and do reconstructed waveform is going to be the Griffin-Lim transform spectrogram. Right, so go ahead and actually apply the Griffin-Lim algorithm to our spectrogram, and we'll end up with our newly reconstructed waveform. And what we want to do is see how they compare to each other. So I'm going to go ahead and plot the visual. We had our Mel spectrogram here. We have our reconstructed linear spectrogram here. Now the problem is when going from the Mel spectrogram to the reconstructed linear spectrogram, it's not a one-to-one mapping, because remember it was binned together. We may have had 512 frequency bins in the original spectrogram, right? We can see 512 here, but because we mapped it to 128 Mel bins, we end up losing a little bit of information because it's not one-to-one. Multiple frequency bins can be mapped to a single Mel bin. So when we're going the other direction, it may not know which frequency bin to map that Mel bin back to because it's not one-to-one. And so some information could be lost here depending on how you set up the Mel spectrogram. And then we can go ahead and compute our audio on the original, on our reconstructed spectrogram. And to do that, what we're going to do is just go ahead and plot it, audio reconstructed waveform, and we know the rate is 16,000, and play it back.
A distinct promise of 100 pounds was made to him if he would have the child ready to hand over to Trevelyan.
Okay, so not bad. It sounds a little robotic, right? But we did reconstruct something, and this could be an artifact of the lack of the one-to-one mapping to go from Mel back to linear spectrograms, and also, of course, the approximation errors from an iterative algorithm of going from our spectrogram to our audio itself. Let's listen to the original one again. That was just regular. I think I just called it audio, so let's just do that.
A distinct promise of 100 pounds was made to him.
That's the original audio. And so this method is okay, but actually not all that much used these days. You're better off using something known as a neural vocoder. So Griffin-Lim can create a reasonable approximation of magnitude spectrograms to audio, but it's not as good as deep learning based methods. So there's a lot of deep learning methods out there, like HiFi-GAN is one we'll implement one day in the future. And in HiFi-GAN, you end up basically learning a neural network to take a Mel spectrogram and produce the audio directly. And these are significantly higher quality than something Griffin-Lim could produce. But either way, let's go ahead and just do a summary table here, just so you can see the flow between all the things that we did. So what we normally start with is a waveform, right? A waveform, right? That's our original data. And there's two ways we can process this. Either one, we do a Fourier transform, right? Fourier transform. And this is going to produce a frequency. And the waveform is time domain, right? Time domain data. And this is going to produce frequency domain data, right? Fully frequency. So in this case, we've lost all of the temporal information, and this is not really a pathway we normally take, especially for speech processing and audio processing for neural networks, because we want to have a mix of time and frequency domain. So let's go ahead and get rid of this because we're not going to really look at it. What we do instead is something known as the short time, let's do it here, short time Fourier transform, which will end up producing something known as the spectrogram, right? Which is kind of like a picture, right? A picture of audio, right? Gives you an image of the audio, essentially. It's a good way to think about it. So we have our short time Fourier transform, we give it to a spectrogram. Now that we have our short time Fourier transform and we produce spectrogram, we typically, for speech specifically, will do a Mel scale, right? Make it closer to human perception, right? So for speech and human listening and stuff like that, we typically convert it to a Mel scale. And so you'll end up with a Mel spectrogram. Unfortunately, this mapping from spectrogram to Mel spectrogram is not necessarily a one-to-one mapping, right? So just keep that in mind. Now, how do we go back? Well, we can go back from the Mel spectrogram to the spectrogram using an inverse Mel scale, right? We take an inverse Mel scale to get back from there to there. And the spectrogram, assuming this is just magnitude, right? Magnitude, because we don't have the phase information, we can approximate the waveform using the Griffin-Lim algorithm, right? That's our approximation. So this is an approx. And these are kind of the main tools you'll be using for speech processing, so it's helpful. When working with neural networks, there's basically two ways. There are more, but the main two ways you're going to see going about is that either either you're passing raw waveforms. So in the wave-to-vec architecture that we'll implement in the future, we'll pass it a raw waveform. So the model takes raw waveform audio and learns something from it. Other architectures like Hi-Fi again, which is a vocoder, or even Whisper, or a lot of the TTS models, to those you pass spectrograms. So instead of passing raw waveforms, you pass it a spectrogram, and then it does some type of neural network stuff on the spectrogram instead. So we're going to be implementing deep speech too, which will be using spectrograms. Then we'll be implementing wave-to-vec, which will be using raw audio, all in the future. This is just supposed to be a high-level overview of kind of some of the different tools we use for audio processing using TorchAudio. And so I will see y'all in the next one.